The last video went through how to calculate the real and imaginary parts and then the magnitude and phase of the transfer function to evaluate it at s is equal to I omega in order to calculate out the Bode plot, essentially the quantities that are plotted on the Bode plots. They did that for s and 1 over s, so some pretty simple transfer functions. So now we're going to continue to develop out all of these very simple and modular transfer functions, and then we'll use these Bode plot combination rules in order to study how to combine these together in order to form the complete Bode plot of a more complicated transfer function. So for now, what we're going to do is we're going to take a look at just this particular case of a single pole. And your goal is to essentially do the same kind of analysis, identify what g of I omega is, substituting in I omega where you see s, then find the magnitude and phase of that, and then try to sketch out what the Bode plots should look like based on those values. So go ahead and give this a shot, and then I'll show you my solution. Okay, so there's a lot on this slide, so let's go through it nice and carefully. So when we're evaluating g of I omega, we're just replacing, every time we see s, we're replacing that with I omega, and so that's what's been done here. So the imaginary, there's an imaginary part in the denominator, which is kind of a no-no, so we want to get that out and put all of the imaginary stuff in the numerator, and so the way we do that is we multiply top and bottom by the complex conjugate. So that's 1 minus I tau omega on top and bottom, and so that's why we get a factor of that in the numerator. And then the magic is that when you multiply by the complex conjugate, you get this real value, which is essentially just the squared real part and the squared imaginary part. So then pulling this numerator down, we get this common factor out front. And then we get the real and imaginary parts. And so from that, we'd like to calculate the magnitude and the phase. So the magnitude is calculated as the square root of the real part squared plus the imaginary part squared. We have this common factor so that it just can stick out front. And then you've just got the real part squared plus the imaginary part squared. Once you square that, you'll realize that you indeed have a copy. You have a square root of the thing that you have in the denominator, which allows you to nicely solve it out to be this value, which is the same thing as 1 over the square root of 1 plus tau squared omega squared. All right, so that's the magnitude. If we'd like that in decibels, then we'd take 20 times the base 10 log of that. So we're just going to take 20 times the base 10 log of this quantity here. That gives us this. We can use some log rules to bring down this minus 1/2 in the exponent to get minus 10 log 1 plus tau squared omega squared. If we take a look at the angle, or the phase, then we take the inverse tangent, we put in the imaginary part and the real part. In this case, remember that we have this common factor, so technically we'd have this divided by the this divided by just 1 plus tau squared omega squared, and 1 divided by 1 plus tau squared omega squared. But since these are common, they cancel out. And so that's particularly clear if you just use atan. So that's then you just divide the real part, or the imaginary part, by the real part. But even in atan 2, you can get rid of these denominators, the common factors. All right, so now let's take a look at how we would go about plotting these. So again, these are going to be sketches. So when omega, so if we look at the magnitude, when omega is small, then the second term, tau squared omega squared, is small compared to 1. So that means that this pretty much looks like minus 10 log of 1. And so the log of 1, the base 10 log of 1 is 0. And so that means that the magnitude plot is going to start out at 0. So let's just kind of reflect on this real quick. Notice that when omega is small up here in the actual magnitude, not the decibels, but the actual magnitude, then omega squared tau squared is small, so this just goes like 1. So magnitude of 1, it corresponds to a decibel magnitude of 0 dB. So when you see 0 dB, think that there is no magnitude change from the input to the output. So that means the input comes in at some amplitude and it comes out in the output at exactly the same magnitude. So there is not a magnitude scaling at low frequencies. So at high frequencies, what happens? So at high frequencies, the 1 term here is insignificant. And so this looks like minus 10 log of tau squared omega squared. And so now we can use our log rules to split this up. This is minus 10 times log of, we'll put omega squared first, and then minus 10 log of tau squared. Okay, we can use our log rules again, so that's really just splitting up this product that's right here. So now we can use the log rules to bring down the 2 factors. So we've got 20 now log of omega minus 20 log of tau. So that's what it looks like when omega is large, and we can forget about this extra 1 here. So that means that this looks just the same as our 1 over s term, where it was going down at a slope of 20 dB per decade. And so that's what you're seeing here. This is a slope of minus 20 dB per decade. So no matter what value of tau you have, it still approaches this minus 20 dB per decade. And there's a lot of different ways to figure out kind of when the transition is. I think the easiest one is to say that the transition happens when in the log this term, which is 1, is comparable to this term. So it's the value of omega for which these things are comparable. That happens when omega is 1 over tau. So when omega is 1 over tau, then you've got 1 plus 1, and these are kind of relatively equitable terms. Once omega is bigger than that, then it dominates, and that's when you start getting this 20 dB per decade slope. So the breakpoint then is going to be at this 1 over tau. And so that kind of indicates where it really changes from this kind of 0 regime to this 20 dB per decade regime. That's going to connect with what we do in the phase plot. So in the phase plot, the inverse tangent, remember, so I always think about it in terms of in this case, the real and imaginary parts. Oops, imaginary parts. So in this case, the real part is always at 1. So this is 1. And for small values of omega, you have small negative values. So that's something like here. So at that point in time, the overall vector looks like this. And so that means that the vector that corresponds is like this. And so for very, very small omega, that's going to look like 0. And so that's why this plot, the phase starts at 0. So as omega gets bigger and bigger, as soon as omega is equal to 1 over tau, now you're at minus 1. So now you're at minus 1, 1, and that's this point, and that's when this vector is down at an angle of 45 degrees. And so at this kind of break point, that's where we hit 45 degrees. And so at 45 degrees, that's where you're intersecting where this break point happens. So that's how that happens there. Once omega is really large, and that means that you're taking this point going further and further out here. So omega is very large. Now you're getting essentially an angle that's getting closer and closer to minus 90. And I should have said up here, this should have been minus 45. So now you're getting closer and closer to minus 90 the further this point gets larger on the negative imaginary axis. So for that reason, this is going to approach to 90 degrees. So that's why all of these essentially approach 90 degrees. So again, calculating out the real and imaginary part, getting the magnitude, then the magnitude in dB, and then the phase, and then sketching essentially out what happens at small frequency values and large frequency values.